What's up guys, welcome to another video of the course Dynamic Programming for Beginners. This is part 9 and this is crazy because I can't stress enough how happy I am. We've got so far and it's a day and night compared to where we were just about a month ago. I never thought in my life that I would dedicate so much time to dynamic programming and upload so many videos on YouTube. If you think about it, 9 isn't really that much, but to me, it's a lot, trust me. I'm pretty sure you know what I mean. It's insane. And by the way, thank you so much for watching these videos. Thank you for your comments and thank you for your upvotes. Believe it or not, but the only motivation that I have is your feedback. I would never get that far without you enjoying these videos, liking, commenting, and all that. So huge props to all of you guys. Anyways, let's get to work. So today we're going to review yet another problem, but what's interesting about this specific problem is that it's a super popular interview question at Amazon. So if you're applying to internship at Amazon, or you just graduated from school and this is your first time you're looking for a job, or if you are an engineer with, let's say, 5 or 7 years of experience and you want to work at Amazon, you may still get this problem. So you can, as you can see, this is a very popular problem that you can expect to get no matter how experienced you are. So what the problem is about? The problem is about finding the number of ways to reach position XY in a matrix. So the matrix is of size m by n, and the goal is to find the number of ways to get to position XY. So usually the position XY, it's the end of the matrix, right? So this problem is in a way very similar to the climbing stairs problem. So let's review some example, right? So let's say we have a matrix m by n of size, let's say 3 by 5, right? And let's draw this matrix. So here is our matrix of size 3 by 5, 1, 2, 3, and then we also have 5 columns, right? 1, 2, 3, 4, and 5. And usually in such problems, we're starting from position 0, 0, right? 0, 0. So we're here and we need to get to mn, right? So we need to get to the end of the matrix. And in this specific problem, we are allowed to go either to the bottom, either down, or to the right, right? So for instance, if we stand here, we can go either to the bottom or to the right, right? Once we get here, we can go either to the right or down. Once we go here, we can go right or down, right? So the goal of this problem is to find the total number of ways to get to XY. Okay, so how do we solve this problem? Well, first of all, this problem, as you can see, it's very similar to the climbing stairs problem. And as usual, let's try to solve this problem kind of like from, well, first of all, let's maybe use the framework that, that we know about how to solve dynamic programming problems. So the first step in the framework is to define the objective function. So what is the objective function here? So we have 2 parameters here, right? We have I and j, right? It's no longer just f of I, it's f of I, j. So f of I and j is the total number of ways to get to position I, j, right? Okay. Second, in the second step, we need to identify base cases, right? So let's solve the problem again when the computer is not even needed. So first, let's say we want to solve the problem for the very first, for the most simplest use case, when the matrix is, let's say, of size 1 by 1, right? 1 by 1. And let's draw this matrix. This is the matrix of 1 by 1. And we're here. And we're allowed to go either down or to the right, right? But we can't go anywhere because the matrix is super small. It's very small, just 1 by 1 size. So how many ways to get to 1 by 1? It's just 1, right? We don't have to do anything. It's very similar to other problems we solved. Okay, so let's review one more use case. Let's say the matrix is of size 2 by 2, right? So the size of the matrix is 2 by 2. So again, we're here and we need to go to the position 1, 1, right? So how many ways to get there? So the first route is this, and the other route is that, right? So we can go either like so, either that way or this way, right? So the total number of ways is 2. Note the or that I just mentioned, so you can go either this way or the other way. So the problem is very similar to the climbing stairs problem, in which we had to find the total number of ways to reach the top of the staircase, right? And we were allowed to make either 1 or 2 steps at a time. So when we have or, it means that we need to sum, to add things together, right? We need to use the sum operation. So we basically add all the ways, all the routes together. Okay, cool. So we know that we'll have a sum operation in the transition function, right? So which is the third step. So the second step, we kind of like identified base cases over here, right? So we know that. Now what about the transition function? So as usual, when we want to find the transition function, let's think about the problem as if it's already solved, right? So let's say we're standing here. The problem is already solved. How could we get there? So the first option, the first way is we could get there from above, right? The other way we could get there is from the left. So either from here or from there. So either or, right? Again, so this is exactly the same as here. So what do we need to do? We already solved the problem for this use case, right? And it means that the same approach can be used to solve the problem for any mn, right? In this case, it was just 2 and 2, and we can apply the same thing here. So what's the coordinate of this cell? This one is I minus 1, and that one is I j minus 1, right? So the transition function to this problem is f of ij equals f of I minus 1j plus f of I j minus 1. And that's pretty much it. This is our transition function that we can use to solve this problem for any mn. Okay, so this is very easy to code, right? We know how to code this type of problems. Now let's say the interviewer tells you something like, okay, that's great. Now let's complicate the problem a little bit. Let's say that you have certain, cells. You're not allowed to step on those cells, right? So how would you solve this problem? Again, this is very similar to climbing stairs problem. If we have cells that we're not allowed to step on, right? It's similar to the red stairs. It means that in these positions, we won't count anything. So here the solution would be 0. So if f of I minus 1 j is, so, well, first of all, if we have cells that we are not allowed to step on, then it means that we would need to store them somewhere, right? So we would have it's additional information which we need to store somewhere. So we would need some sort of array with, to store these locations, to store this cells. So let's say we have, something like, I don't know, like bad cells, whatever, bad cells. And this would be an array of, in this case, it's 0, 1, 2, 0, 3, comma, 1, 2, 1, 2, right? So every time we calculate I minus 1j, ij minus 1, we check, is I minus 1j part of the bad cells array? If yes, then don't do that. Then basically say that this is 0. If ij minus 1 is part of bad cells, then again, f of ij minus 1 would be 0. So this one is pretty simple as well, as you can see, right? The transition function stays the same, it's just we would have a few more if-else conditions. We would have, I think, 2 more, right? We would have to check for I minus 1j and ij minus 1, whether they present in the bad cells array. Awesome, so this one is easy to code as well. Now, let's say the interviewer tells you, like, hey, this is all great, but now find the most profitable path to position Mn, right? So we have the same matrix of size 3 by 5, but then in each cell we have some coins, right? So let's say this one is 1, this one is 2, 1, 1, 2, and then let's say, actually let's say this one is 3, this one is 2, 5, 4, 4, 2, and then 1. And this guy's 1 as well. Right? So we're here, and we need to get to position Mn. So we need to get there, but we also have to collect the most amount of coins. Which visually, we can immediately see that the best route to get there would be like that, right? This would be the best route. So you would go kind of like to this cell first, then to that cell, and then all the way to the right. Great. But how would we do it algorithmically? What's the algorithm? What's the transition function here? In order to get the transition function, we have to think in the exact same manner. Let's say the problem is already solved, right? So let's say we're at the end of the matrix. Where could we get there from? Well, we would got there from a position which is so far most profitable, right? Again, we have the exact same constraints. You're allowed to go either down or to the right. So if we're here, we could get there from either from here, right, from the top, or from the left. But we are no longer counting things, we're just collecting, collecting profit. So we want to get the most amount of profit. So we could review, let's say we would review this small problem, right? Like if the matrix is just this size. We would have to get get to the last point from the most profitable so far, right? So it means we would get from the maximum between the top one and the left one. So it would be the max of f I minus 1 j and f of, you see I use different notation here, f of I j minus 1. Okay, so that's great. So we got to the path, right? We've got the maximum so far, but we also have to pay the current amount, right? To jump to this location. So what would we pay? We would say, okay, so plus whatever we need to pay. And we need to pay plus f, or let's say d, right? Some d of I j. So D denotes current prices, current cost to get to a certain cell. So the transition function, this is basically the transition function. So the f of I j equals maximum f of I minus 1j, f of I j minus 1, plus the price to jump to the current cell. All right, so I've got all of the problems over here, so I created tests and let's code it up. So let's do it as fast as possible. So we need to write a lot of code. So the first thing, we need to find the total number of ways to reach the end of the not staircase of the grid, right? So we are starting from here, and the end is over here. The transition function, let's recall it, was f of ij equals f of I minus 1j, right? Plus f of I j minus 1, right? So one thing here is that we have to be mindful about boundaries. So each case, like this guy, for instance, we only want to run when I is greater than 0, right? So when I is greater than 0, and this one when j is greater than 0, because if j is 0 here, then we'll go out of boundaries, and the same for I. Okay, so let's code it up. So I'm going to create an array of arrays to hold the values for subproblems, and now I need to initialize each column. This is just a thing in Go. I unfortunately can't initialize dpmn right away. So okay, so we have our array. Now we can start. Well, now let's specify base cases, right? So dp of, when we're at the beginning, we don't have to do anything, so it's just one way to get there. Now let's loop over the array while I less than, we can say m, and then for j equals 0 while j less than n, j plus plus. And now all we have to do is basically just apply our transition function and be mindful about boundaries, right? So we can say something like, if I is greater than 0 and j is greater than 0, so this is like the regular, this use case, right? Then dp of ij equals dp of I minus 1j plus dp of ij minus 1, right? Now, if let's say I is greater than 0, but j is 0, so then dp of ij equals, we can just say dp of I minus 1j, and that's it, right? Otherwise, if j is greater than 0, but I is 0, then we can just swap and we say dp of I j minus 1. And the answer should be in dp of m minus 1 n minus 1, if I'm not wrong, because we start from 0, right? So if we have a matrix of size 1 by 1, the answer is in dp of 0, 0. Let's test it and see if it works. Missing return at the end. What is the problem here? Return. No, I've got the return here. What is it? Oh, it's other test cases failing here. Okay, so let me fix this real quick. So this one, let's say return 0, and this guy return 0 as well. And now let's rerun. Awesome, so both tests passed, right? So the small matrix 1 by 1, the answer is 1, and then 3 by 4, the answer is 10. Awesome, so now let's move on. The problem number 2. So let's say we have obstacles now, right? So we have the exact same matrix, but now we have obstacles. So if it's 1, for instance, it means we can't step on this cell, right? So the best path here is starting from here, and then we would go essentially like so, right? All the way to the bottom, and then all the way to the right. So we only have one path in this matrix, right? So let's code it up. The exact same thing. So we create dp of size m by n. I don't have m here, so I have a grid which would represent our matrix. So when it's 0, it means we can step on a cell. If it's 1, it's an obstacle. So we'll say just length of a grid. Or we can do the other way. We can say m equals length of a grid and n equals length of a grid 0. Now this is m for I range dp of I equals make int n. Okay, so we have our solutions array. Now we can loop over dp while I less than m, I plus plus, for j equals 0, j less than n, j plus plus. And let's also specify base cases. So when dp of 0, 0 equals to 1, right? And we will also return dp of m minus 1 and minus 1. So what's the difference between this one and the previous one? We mentioned that the only thing we would have to do, let's copy the transition function. So the only thing we would have to do is to check that if we have an obstacle, then we don't want to count this as a subproblem, right? So we would say if if the grid where we want to, if the next cell that we're about to step on is 1, then the solution to this subproblem is 0, right? And we can just continue and don't do anything. So that's pretty much it. Let's see if the tests are working, passing. Oops, not debug, test. Great, so all the tests passed. Oh my god, what is this? All the tasks passed. So now the last one is slightly different, right? We want to find maximum profit in a grid. So this is our grid. This is an optimization problem, right? We are finding the maximum of a function. So we are starting here and we want to finish at the end. We want to find the maximum amount of coins we can collect as we go, right? In the exact same constraints, we can move either down or to the right. So the best path here is, in fact, we move all the way to the bottom and then all the way to the right. Cool, so let's code it up. We have a grid that represents our coins, that contains the values for each coin. And I'm going to copy this thing because it's annoying. Now let's loop over the array, and then also let's recall our transition function. So the transition function is f of ij equals to the maximum, right? So when we're at the end, when the problem is solved, we can collect maximum from the cell to the left or from the cell to the top. Is that the right way to say it? So it's the maximum of f of I minus 1j and f of I j minus 1. And then plus, we need to pay
to step to the last cell, right, to the cell itself. So plus, it was d of ij, right? And d represents the price, the cost we have to pay to step on the cell ij. In our case, it's grid ij. So while I less than m, I plus plus, for j equals 0, j less than n, j plus plus. And now the exact same thing here as in the previous two problems. So when I is, we have to be mindful about boundaries, right? So when I is greater than 0 and j is greater than 0, we can apply this guy, right? We can say dp of ij equals maximum between dp of I minus 1j and dp of I j minus 1, and then plus grid ij. Else, if I greater than 0, right, meaning j is 0, we can just say that dp of ij equals dp of I minus 1j plus grid ij. Else, if j greater than 0, we can say, I'll just copy, I j minus 1 plus grid ij. And then we'll return dp of m minus 1 and minus 1. And I think that's about it. Let's see if the... By the way, you see, we don't have max function here. Let me define it real quick. Again, it's a shame that Golang doesn't have those things. Actually, there is a function max in Golang. It's just in the package math. But it's not working for integers, just for float, I believe. Cool. So, and then the last thing here, actually, we can, you see, like we have grid ij, we always add it no matter what. So we can say dp of ij is grid ij, and then instead of like having it here, we can just add it like so. Okay, so let's run the test and see if the code is correct. Boom, everything is good. So, so we've printed out the maximum profit, right, that we can collect. So let's actually test another use case when, let's say it's simple test 2. And so the path that we just went through was 3, 4, 4, 2. Right now, if I do something like this is 100 and this one is 50, now the best path is 0, 2, 2, 50, 100, 0, right? So this is, what is it? 154, right? So let's see, 154, and run the test. Awesome. So the simple test 2 is passed as well. So I'll give you guys the homework. So in this problem, we printed out the maximum profit. Now, what is the actual path, right? Can you try to figure out, and can you return the actual path, the coordinates of the of each cell? So this is the homework for you, and we'll review it next Sunday. Enjoy the rest of your weekend, and I'll see you soon. Take care, guys.